Hi everyone, it is Monday, May 23rd, and we are in IC, and it is official. We are starting the final study guide. From the crowd, we have some special requests. They want to see question number 4, 10, 16, and 19. So we're going to go ahead and get started. Let's check out number 4 first. Okay, so number 4 says, what is the empirical formula for a compound that has 8.65 grams of iron and 3.72 grams of oxygen? Alright, so this has to do with empirical formulas, and the only way that we can get empirical formulas is through figuring out the mole ratio between the elements. So sometimes they'll start these problems off with like a percentage. And if you do have a percentage, just assume that you have changed the percentage to grams, like change the symbol percent to a gram, and then calculate moles straight off from there. But here, we don't have percentages. They started you with mass. So we're going to jump right into the very first step. What you guys are going to do is you're going to change those masses into moles, because formulas like H2O, CO2, they're just based off of mole ratios. All right? So looking at the periodic table, molar mass of iron is 55.8 grams per mole. So always cross cancel. So I'm going to put the 55.8 grams down on the bottom, 1 mole on the top. Oxygen's molar mass is 16.0 grams per mole, 1 mole on the top. All right, so let's see what we get here. Okay, and then 3.72 divided by 16. This gives me 0.23, and if you want to be careful with your sig figs, you can say 3 moles of oxygen. You're looking at those ratios and you go, huh, that doesn't make any sense. Those are nasty ratios. If you don't see where the whole number ratio is coming from, this is the next step. You have to divide by the lowest value you've got. Do you guys remember kind of thinking about that? It's been forever since we've done that. Yeah, question. The question was, wouldn't the mass of oxygen be 32 instead of 16? But the thing you have to remember is that we're not talking about oxygen gas. This is one of those weird ones where you have analyzed a sample of a compound, and that compound has some iron atoms in there, and it has some oxygen atoms in there. So this isn't oxygen gas. This isn't, like, you would never double the mass. This is percent composition getting to an empirical formula. Alright, now that you guys know so much, it's going to be really hard to remember all those tiny stupid little rules. Alright, so this is per gram per mole, okay? Alright, really good question. I'm glad you asked. Alright, so what we're going to do is divide by the lowest value that we got, which is 0.155. So I'm going to do that to both of these. And let's see if we get a cleaner number out of these. Obviously that'll be 1, but let's check the other guy. 0.233 divided by 0.155. This will give me about 1.5. It's actually 1.503, but 1.5 is about right. So when you look at these two quantities, you know, you might be able to see that you do have a much cleaner ratio, but it's not perfect. We would never say iron 1, oxygen 1.5, would we? So what can you do at this point after you divide by the lowest value? Do you remember what you can do if you still don't have a clean value? You can multiply, that's right. So what can we multiply both of these guys by in order to get a cleaner ratio? You guys can multiply this by 2. Check this out. So the iron will turn into a 2. 1 times 2 is 2. And then 1.5 times 2 is a 3. So that'll give you a formula for iron. If you look, iron, you've got 2 of them, so I'm going to put a little subscript of 2 after the iron. And then for oxygen, it looks like you have a 3. So we're going to go Fe2O3. And that right there is your empirical formula. So coming back to the original question, just make sure you answered it all the way. It says on question number 4, what is the empirical formula for a compound that has this much iron and that much oxygen? So it sounds like we answered it completely. Alright, so question number 4 is done. Let's go to question number 10. Question number 10 says, how many moles, molecules, atoms of hydrogen, atoms of oxygen are in 134.5 milliliters of water? Alrighty, and these are all the things that we have to figure out. We have to figure out how many moles, how many molecules, how many atoms of hydrogen, how many, hold on, it keeps going, how many atoms of oxygen, and did I get it all there? Yeah, okay, so 4 questions. Alright, so this goes back to doing dimensional analysis with your moles. I think this was what we called Unit 5. So Unit 5 was all about dimensional analysis with moles and mass and all of that crazy stuff. So on your study guide at the very bottom, there's a little, let me pull it up here, is the second semester review. Here we go. So down at the bottom, there was this picture that I gave you. Okay, it kind of looks like this. So this guy right here is kind of like a little helper to remind you how to get to all of the different things with the mole. So in this particular problem, we started you with volume, and we want you to go to moles, we want you to get to atoms, right? So let's go back to the original problem here. And on question number 10, it says, how many moles, molecules, atoms, blah, 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 are in 134.5 milliliters of water? Now, here's the thing that it didn't say. This is why we have to be kind of careful. Did it say that it was a gas at STP? No, it did not. So unless it says that, you can't use that one conversion for gases, which was 22.4 liters per mole. It didn't specifically say that this is a gas at STP, so we're going to assume that this is water in the liquid form. Alright? So let's start with the quantity given to us, and remember, it didn't say that this was a gas at STP, so what do you know about 1 milliliter of water? That might help us get started, because we can't use 22.4 liters per mole. Do you guys remember its density? What's the density of water? It's 1, right? What does that mean? If I have 1 milliliter of water, how much matter will be stuffed inside that 1 milliliter? 1 gram, right? Because that's the density of water. Each milliliter of water weighs 1 gram, and that's specific to water. So each milliliter, 1 milliliter, is equivalent to 1 gram. Do you guys see how I converted my milliliters to mass? Alright, so I've got mass, but we kind of need to get to the point where we're answering some of these questions. So we're technically with grams. You see how grams is sitting there on the top? What do you think I'm going to do with those grams? What am I going to convert that into? Moles, that's right. So the molar mass of water, I think you guys have it memorized. It's 18 grams per mole. So I'm going to put the 18 grams down on the bottom, and I like to always take my molar masses to 1/10 of a gram. We're going to call that 1 mole of water. Now if we stop right here, we're going to answer that first problem. That first question wants us to get moles, and that's what we did. Alright, so 134.5. I'm ignoring all the ones, and I'm just going to divide by 18. I'm keeping with, as you can see, I've got 3 sig figs down here. The density of water is exactly 1, so this kind of doesn't count for sig figs right here. This guy's got 4 sig figs, so I'm going to reduce this to 3 sig figs. Here's what it says on the calculator. 7.47222. And I want 3, 1, 2, 3. So technically the number of moles here would be 7.47 moles. Alright, so we got our first problem there. Next question says, how many molecules? Alright, well what I'm going to do is I'm going to actually come back to my original problem that I set up, and instead of stopping here, I'm going to keep going. I'm going to keep going here, okay? Alright, so I'm on moles of water. If you look back at this little guy, if you're on moles and you're trying to get to molecules, you see that conversion right over the top of this area? it says that 1 mole is equal to 6.02 times 10 to the 23rd particles. Those particles could be atoms, molecules, or formula units. Well, water is a molecule. So in 1 mole of water, you see I'm cross-canceling moles, there would be 6.02 times 10 to the 23rd molecules of water. Right, and the moles will cancel. So redo the problem. If you still have the answer stored from the previous one, you can just use that. I still have my answer on my calculator. It says 7.472222222222 right now on my calculator. And I'm just going to go times 6.02 e to the 23rd. Okay. This is what I got. 4.49827777, and it keeps going, times 10 to the 24th. Hold on, let me scoot this over. Alright, still going to reduce that to 3 sig figs. So, 1, 2, 3. Do you guys need to round that last value right there? Do you guys need to round the 9? Oh no, so you got a 9 that rounds up. Do you guys remember what you need to do? The 9 will turn into a 0, and then what changes? Yeah, the 4 changes to a 5. So the 9 will change to a 0, and the 4 will change to a 5. So this will give you actually 4.50. We're going to include the 0 at the end because it is significant, because it's after a decimal. And then we're going to go times 10 to the 24, and this is how many molecules you have. There we go. Now we haven't finished the problem yet. They still want you to go to atoms of hydrogen and atoms of oxygen. That's what this last part is all about, where it says parts of a particle. So the particle that we had was a molecule, and molecules are made up of, well, atoms in a bond, right? So think about water. How many atoms are of, let's do hydrogen. How many atoms of hydrogen are in one molecule? So here's H2O. How many atoms of hydrogen do you have in one molecule? You have 2. So if we take this right here, and you see how I stopped, I'm actually going to keep going. So here's what we need to do to end this. We know that if we have one molecule of water, that there would actually be 2 hydrogen atoms. So this is kind of like a ratio. For every 1 water molecule, there would be 2 hydrogen atoms. So we can use ratios like that to do an extra step. We know that if we had 1 molecule, you see I'm cross-canceling the word molecule, 1 molecule of water would have 2 hydrogen atoms in there. Alright, so if you kept that answer stored on your calculator from the previous set, all you have to do is just go times 2. And on my calculator, this gives me 8.99655, etc., times 10 to the 24th. We still only want 3 sig figs. This ratio right here is a perfect ratio, so we're not going to count it for sig figs, okay? 1, 2, 3. Looks like you need around that 9. That 9's going to turn into a 0. That 9's going to turn into a 0. What does that 8 turn into in the very front? A 9. So this would give us 9.00, I'm sticking with 3 sig figs, times 10 to the 24th hydrogen atoms. Okay. Now, how do we get oxygen? Well, this ratio up here, right here, is for hydrogen. What do you think the ratio is going to look like for oxygen? Yeah, 1 molecule of these is actually going to be equivalent to just, it only has 1 oxygen atom. So the ratio at the end, instead of having a 2 right here, you'll have 1 oxygen atom. So it's kind of like this answer right here. It's going to be the same because it's times 1, right? So 4.50 times 10 to the 24th oxygen atoms. All right, there you go. You got number 10. Okay, let's see what else they wanted me to do. Number 16 is what they wanted. So we'll do number 16. Ooh, 16 is pretty long. We'll see how far I can get, okay? Alright, it says balance this equation And then it talks a lot about if I produce this, if I produce that, blah, 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 blah. It's got 1, 2, 3, 4, 5 different parts to that question. So why don't we go ahead and get started, and if we get cut off, we'll pick up on this question next class. Here we go. So first off, it wants it balanced, so we'll get there in just a second. Oh, that's funny. I gave a product that's soluble, but I labeled it as a precipitate. That's just lovely. Oh well. We'll just pretend that didn't happen. Maybe one of these days I'll fix my final study guide. Oh well. Alright, so balancing this guy. Do you guys see this nitrate wrapped in parentheses with a 2? That means that you have 2 nitrates, and here's my NO3. It's not wrapped in parentheses. So if I'm looking for 2 of those, I'm going to have to put a coefficient of 2 right there. And I'm checking everything. Looks like that's all you had to do to balance it. Alright, here's part A. It says, if I produce 6.5 moles of MgNO3, this is part A. If I produce 6.5 moles MgNO32, how many moles of K2SO4 are also produced? Alright, so when you get confused on these, remember you still have this little guy right here to just kind of help you out with mole conversions. But do you guys remember that other one that we used for chemical reactions? This is specific to stoichiometry. And there was this other one that I used to use with my students. Hold on. This one. Okay, this one deals with chemical reaction stoichiometry. Anytime you're doing math problems where there's like a stoichiometry type aspect to it, you may want to refer to this one, okay? So in this question it says, if I produce 6.5 moles of NgNO3, how many moles of K2SO4 did I also produce? So you're going from moles of one of these substances to the moles of the other substance. In order to do that, looks like you need to go through a mole-to-mole ratio, which comes from the balanced chemical reaction. Alright, so all we need to do is look at the ratio between this guy and that guy. What's the ratio between the two of them, guys? It is 1 to 1. So if it's a 1 to 1, that's so easy. The answer is actually 6.5 moles. Easy. Didn't even have to do any math on that one. Alright, let's do part B. If I have 14.6 grams KNO3, how many formula units of MgSO4 do I need? MgSO4. Alright, so you're starting with mass of KNO3, and they want you to go to formula units of MgSO4. So looking at this guy, they're starting you with mass of A, and they want you to end in formula units. That would be your particles of B. So you need to do the whole thing here, okay? Alright, so we're going to start with the 14.6 grams KNO3. And guys, a traditional stoichiometry problem has a certain number of steps. You'll be changing the mass to moles, you'll be doing a mole-to-mole ratio, and then you'll be ending with formula units, which is the use of Avogadro's number. This is a traditional stoichiometry problem right here. Alright, so let's get that KNO3 molar mass. Potassium, be careful, is 39.1. Nitrogen is 14, and oxygen is 16 each. I got 101.1 grams per mole, so I'm going to put the 101.1 grams down on the bottom to cross cancel, and that is equal to 1 mole. Alright, look at the balanced reaction. We're trying to go from KNO3 to MgSO4. Here's KNO3, there's MgSO4. What's the ratio there? It's not 1 to 1, it's actually 2 to 1, that's right. So follow KNO3, we always cross cancel. KNO3 is right here, and there's a 2 in front for a coefficient, so I'm going to put a 2 down here. So for every 2 moles of KNO3, we're doing the mole-to-mole ratio here, you'll need 1 mole of MgSO4. See how mass canceled, now moles are canceling. Alright, we're trying to get to the formula units of MgSO4. So come over here. Basically where we're at is we're at the moles of the other guy, and we're trying to get to formula units. So as you can see, we need to use Avogadro's number at the very end here. So for every 1 mole of MgSO4, you're going to have 6.02 times 10 to the 23rd formula units. Remember, formula units are just kind of like ionic compounds. That's what they are. We only say formula unit when we're talking about ionic compounds. They just basically want to know how many compounds you got. Alright, so I'm going to take the 14.6 and I'm going to divide by 101.1. Divide again by 2 because that 2 is on the denominator. Denominator means divide. And then multiply that by Avogadro's number. I got 4.3467, etc., times 10 to the 22nd. So let's check your sig figs. Mole-to-mole ratios, like this guy right here, do not count for sig figs. This one's got 3, this one's got 4, this one's got 3. We should reduce to 3. 1, 2, 3. What do you think I'm going to do that number 4 there? Yeah, round at 4.3.